Hello, AP Chem students, and welcome to topic 8.3, weak acid and base equilibria. The learning objective for today is 8.3.a, explain the relationship among pH, pOH, and concentrations of all species of a monoprotic weak acid or weak base. So if you remember, we have already talked about strong acids and strong bases. Strong acids and strong bases fully dissociate, whereas weak acids and weak bases only partially dissociate. So only a small percent of the molecules actually ionize to produce H3O plus or OH minus, as you can see on the images over here. So most of the molecules remain in their undissociated form, which you can see in both cases as gray. And then a part of them will actually proceed to form the products. Because of this, the concentration of H3O plus or the concentration of OH minus is less than the initial concentration. A large majority of the weak acid or weak base particles remain undissociated, and it is necessary to use ice tables to determine the concentration of the H plus or the OH minus before you determine pH or pOH. So this is an application of equilibrium, and this is why this unit follows Unit 7. In general, the 5% rule does apply, and X can be ignored if the ratio of the molarity of acid over Ka or the molarity of base to Kb is greater than 100. So let's look at the equilibria here. So with weak acids, the dissociation of a weak acid is described by the acid dissociation constant, which is Ka. So we can write the expression of the dissociation of a weak acid, and we would write that by adding water is a reactant, and then it would produce your A minus and then hydronium, which remember is the conjugate acid of water, and then your A minus is the conjugate base, and so then this would be your Ka expression. And then, come on, computer. Similarly, the dissociation of a weak base is described by the base dissociation constant. As you can see, the equation is written here where B is that weak base, and then we add water, and then the way the weak base works, so a weak acid and a strong acid actually work pretty similarly in that they both produce hydrogen ions. A weak base, remember, is a hydrogen, or bases in general are hydrogen ion acceptors. And so that base actually pulls the hydrogen off of water. And so that's how the hydroxide is formed. And the hydroxide ion is, of course, the basic particle. It took them a little while to figure that out. They realized that there was some weak base. They knew about the existence of weak bases before they could determine the mechanism through which those weak bases actually acted. So that's kind of interesting. So then there's your Kb for your weak base. So just like pH can be calculated to give whole numbers and also to give numbers that kind of fall on the scale of 1 to 10, which is easier for our brain to think about, we can we can make it easier to compare values for acids and bases by using pKa and pKb. Okay, so pK is equal to the negative log of your Ka, whereas pKb is equal to the negative log of your Kb. So for conjugate acid-base pairs, a special relationship exists. So what we mean by that is, like, if you have ammonium, for example, as your weak base, and then, ammonia, and then its conjugate acid, ammonium, their Ka and Kb's would multiply together to give you Kw. And so then that allows us to also derive this equation, which is pKa plus pKb is equal to 14. Remembering that Kw is a constant. At 25 degrees Celsius is 1.0 times 10 to the negative 14. So I have a practice here for you. So practice 3. Hypochlorous acid, HOCl, is a weak acid commonly used as a bleaching agent. The acid dissociation constant Ka for hypochlorous acid is 3.2 times 10 to the negative 8. So part A, write the expression for the dissociation of HOCl. Part B, write the expression for the equilibrium constant for HOCl. Part C, calculate the concentration H plus of a 0.14 molar solution of HOCl. If you want to try this on your own first, please pause the video now and go through the answer. Okay, so I did give you the question kind of small at the top again here for reference. Let me move my face out of the way. Here we go. All right, so first thing we're going to do is we're going to write, okay, I didn't go far enough out of the way. Move it over there. We're going to write the expression for the dissociation. And so we're going to have HOCl that is going to be reacting with water. Okay, so first write, can't go anywhere. There we go. Let's try this. Write the dissociation equation. So it's going to look like this. So HClO is going to react with water to form hydronium and ClO minus. if you were doing this from scratch, this is the first thing you would do. We see it a bit more scaffold now in the exam, as you see in this question. So then part B of the question asks us to do step 2, which would be to write the expression for the Ka. So then that would be Ka is equal to the concentration H3O plus times the concentration ClO minus, all divided by concentration of HClO. So then to calculate concentration H plus, the next thing we do is fill in the ice table with the given information. So we know that we're starting with 0.14 molar for HOCl, and then before it dissociates, we have 0 molar of our products. So then we're going to have a minus X plus X plus X situation, and then that will give us these equilibrium values. Now, we're going to substitute for the E line in the Ka expression. We're going to be able to ignore the minus X in the reactants because the ratio of the molarity of acid to Ka is greater than 100. So the starting molarity is more than 100 times larger than your Ka. So we're going to ignore the minus X. So then 3.5 times 10 to the negative 8th, which remember is our Ka from our prompt, is equal to X times X over 0.14. So then now we can use that. We can solve for X by rearranging. So we'll multiply both sides by 0.14 and then square root that. And we get that X is equal to 7.0 times 10 to the negative 5th. And then we can use that to report our concentration of H plus for this solution. So the concentration of H plus is equal to X, therefore 7.0 times to the negative 5th is our answer. If this question asked you what the pH of this solution would be, you could do one more thing, which is a simple add-on at this point, which is to do the negative log of that concentration. You would get 4.2. Again, this question did not ask for this piece of information, which is why I kind of graded out a little bit for you. So the value of X over there is actually the answer. So we can compare acid and base strength by using Kas or Kb. So we can make comparisons. The higher the Ka or Kb, the stronger the acid or the base. Now remember, when you're thinking about weak acids and weak bases, you're going to have negative exponents. And so negative exponents, the smaller the value of the exponent. So the smaller the magnitude of the exponent, the stronger it's going to be. So an acid with a Ka of 10 to the negative 3 is stronger than an acid with a Ka of 10 to the negative 5, right? Okay. So we can also use percent ionization of a weak acid or weak base to make strength comparisons. We can do this in one of two ways. So you could be given the pH of the acid, and from that you can determine your hydronium concentration and divide that by the original concentration. So remember that a percent is a part over a whole. And so when you're doing the percent ionization, your part is the extent to which it ionizes, and the whole is the original concentration. So you have to figure out how much is produced in the ionization process. And so one way to do that is with pH. The other way to do that is to use the initial concentration of the acid and the value of the Ka. And to do that, you would have to do an ice table. So you would do an ice table, and then you would solve for X, and then you would take X and divide it. Where'd I go? There we go. By the original concentration to get your percent ionization. All right, whoops. Too far. Back one more. Nope. Okay, there we go. Note about solutions with multiple acids and bases. Sometimes you have more than one. Why? There we go. Sometimes you have more than one acid or base dissociation that can be taking place in the same solution. If that happens, what you're going to do is you're going to evaluate the equilibriums by looking at the Ka or the Kb values and see which one's going to dominate. So at least, especially in AP, you're going to have a Ka or Kb that's going to be much stronger than the others. And so that will dominate. In a lot, it's a little bit like the way that we can ignore X, because if you have a Ka that's like 3 times larger than the next largest Ka, then by the time you add any appreciable dissociation, it's going to either be less than 5%, and so then we kind of ignore it, or sometimes it's such a small contribution that once you take significant figures into account, it doesn't even have an impact. So the highest Ka or Kb value will dominate the solution. Okay, so I do have a percent ionization. There we go, practice for you. This is practice number 4. Calculate the percent ionization of a 0.125 molar solution of nitrous acid, which is HNO2. That's a weak acid with a pH of 2.09. So again, if you want to try this on your own first, go ahead and pause the video now. I'm about to go through the answer. Okay. So first thing, remember that pH is equal to negative log of your concentration of H3O+. So this is actually a plug and chug situation. So what we need to find is your concentration of H3O+, and that will tell us the concentration after dissociated, and then you'll divide that by the original concentration. So we're going to plug in for our pH, we're going to rearrange, and we're going to solve for H3O+, which is 8.13 times 10 to the negative third. Then you're going to take that, and you're going to divide by the initial, which is 0.125, and then we multiply by 100, and you're going to get 6.5% ionized, which sounds about right for a weak acid. Most weak acids and bases dissociate less than 10% a lot of the time. That is it for this. So what should you be able to do with this? Well, you should be able to compare strong versus weak acids and bases. Also with particle diagrams. So if that doesn't seem like it's something you could do, you would want to go to, there's a really great set on strong and weak acids and bases. So I'd really recommend you go look at that. Use a Ka expression to calculate the pH of a weak acid or a Kb for a weak base. Calculate the pKa of a weak acid or the pKb of a weak base, and then determine the percent ionization of a weak acid or base given its pKa or pKb and the starting concentration, or also if you're given that pH. And that is it for this one. Kind of a long one. Thanks for hanging in there with me. I'll see you soon for topic 8.4.